Hello and welcome to Computing Fundamentals 2. In this video, I'm going to focus on describing the degrees and neighborhoods of vertices and how the degree of a vertex can be calculated. Finally, we will discuss the handshaking theorem. We introduce some of the basic terminology of a graph theory in this lecture video. We will use this terminology later on when we solve many different types of problems. One such problem involves determining whether a graph can be drawn so that no two of its edges cross. First, we give some terminology that describes the vertices and edges of an undirected graph. By definition, two vertices U and V in an undirected graph are called adjacent or neighbors. In G, if U and V are endpoints of an edge of G, such an edge E is called incident with the vertices U and V and is said to connect U and V. We will also find useful terminology describing the set of vertices adjacent to a particular vertex of A in a graph. The second definition is going to describe the neighborhood relationship. The set of all neighbors of a vertex V of G denoted by the function n of V is called the neighborhood of V. If A is a subset of V, we denote by n of A the set of all vertices in G that are adjacent to at least one vertex in A. To keep track of how many edges are incident to a vertex, we make the following definition. The degree of a vertex in an undirected graph is the number of edges incident with it, except that a loop at a vertex contributes twice to the degree of that vertex. The degree of vertex V is denoted by the degree of V. So let us take an example. What are the degrees and what are the neighborhood of vertices in the graphs G and H displayed in figure 1? The answer is, in G we have a degree of A for node A equal to 2. That's why, because A is connected to F and is connected to B. Now the degree of B equal the degree of C equal the degree of F, and those equal to 4. But the degree of D equal to 1. But for example, in graph G, the degree of G equals 0 because G is not connected to any other node. The neighborhoods of these vertices are, for n of A, we call it the neighborhood of A, is the subset B and F. So on for node of C, we have n of C equal the subset B, D, E, and F. In a graph H, we have degree of A equal to 4 because A is connected to 4 another nodes. And we have the degree of E equal to 6 and the degree of D equal to 5. The neighborhoods of these vertices are n of A is the subset B, D, and E. But there is something we need to notice about node B, where the neighborhood of B equal the subset A, B, C, D, and E. So this is an example just to describe the neighborhood and the degree of vertices in a graph. What we do get when we add the degrees of all the vertices of a graph G equal the combination of V and E, each edge contributes to the sum of degrees of the vertices because an edge is incident with exactly two vertices. This means that the sum of the degrees of the vertices is twice the number of edges. We have the result in the following theorem, which is sometimes called the handshaking theorem. It's called handshaking because of the analogy between an edge having two endpoints and a handshake involving two hands. Let G equal V and E be undirected graph with M edges, then 2M equal the summation of all degree of V where V is element of V. Note that this applies even multiple edges and loops are present. So, as an example, how many edges are there in a graph with 10 vertices, each of degree 6? because the sum of the degrees of the vertices is 6 multiplied by 10 equals 60. It follows that 2m equals 60, where m is the number of edges, therefore m equals 30 in this case. A loop edge gives a vertex a degree of 2. In any graph, the sum of degrees of all vertices equals twice the number of edges. So the total degree of a graph is even. In any graph, there are even number of vertices of odd degrees. Graphs have some special type that we will describe in the following slide. Complete graphs on n number of vertices denoted by k of n is the simple graph that contains exactly one edge between each pair of distinct vertices. So in a complete graph, all nodes are connected to each other. Another special types of simple graphs is called cycles and wheels. A cycle C of n for n greater than or equal to 3 consists of n vertices, and this is going to be from v1 up to vn, but we will notice that the edges are connecting v1 with v2, then vn minus 1 is connected to vn, and then vn is connected to v1. A wheel w of n is obtained by adding an additional vertex to the cycle C of n for all n greater than or equal to 3 and connecting this new vertex to each of the n vertices in C of n by a new edge. Another special type of a graph is called the cubes. In the cubes, we have an n-dimensional hypercube or n cube, q of n, is a graph with 2 to the power n vertices representing all bit strings of length n, where there is an edge between two vertices that differ in exactly 1 bit position. Finally, we can represent a graph in local area network. So a star topology or ring topology can be represented using a graph as shown in figure 7. Thank you for watching this video and see you in the next one.